Glider 5.1 Glider Performance. Let's delve into the intricate world of glider performance, exploring the factors that influence it during various flight phases, launch, landing, and free flight. Our focus will encompass the pivotal elements of design, weather conditions, wind dynamics, and atmospheric phenomena. As we embark on this journey, let's first understand the four major factors that significantly impact glider performance: density, altitude, weight, design, and wind. Particularly, during the launch phase, the power output of the launch mechanism and the aerodynamic efficiency of the glider come into play. Now, let's delve into the crucial concepts of high and low density altitude conditions. High density altitude denotes thin air, often associated with high elevations, low atmospheric pressure, high temperatures, high humidity, or a combination of these factors. Conversely, low density altitude signifies dense air, characteristic of lower elevations, high atmospheric pressure, low temperatures, and low humidity. Understanding density altitude is vital, and pilots must assess it before a flight. Charts specifically designed for this purpose aid in determining density altitude based on field elevation, altimeter setting, and temperature. These calculations are fundamental for assessing glider performance during different weather conditions. Atmospheric pressure fluctuations also play a pivotal role. A drop in barometric pressure leads to reduced air density, subsequently increasing density altitude and impacting glider performance negatively. Conversely, a rise in barometric pressure results in enhanced air density, lowering density altitude, and improving takeoff and climb performance. As we ascend in altitude, air density decreases. The atmospheric pressure acting on air diminishes, allowing molecules to spread farther apart. This phenomenon leads to an increase in density altitude, reducing glider takeoff and climb performance. Temperature alterations have a profound effect on density altitude as well. When air heats up, it expands, causing reduced air density. This, in turn, diminishes takeoff and climb performance while increasing the required runway length for landing. To illustrate these concepts, consider the METAR reports for Love Field, KDAL, and Denver International, KDEN, airports. Despite similar altimeter settings, temperatures, and dew points, the computed density altitude for Love Field is 1,774 feet, whereas for Denver, it soars to 7,837 feet, an almost twofold increase in density altitude compared to Love Field. Now, let's explore the profound impact of wind on glider performance, dissecting its influence on various aspects of flight. Wind dynamics play a pivotal role during the launch phase, affecting the ground roll required for takeoff. A headwind shortens the ground roll, while a tailwind elongates it. Crosswinds during launch necessitate precise procedures or control inputs to maintain the correct runway tracking. As we transition into cruising flight, the interaction with wind becomes even more apparent. Headwinds reduce the ground speed of the glider, leading to a slower actual movement over the ground. Conversely, tailwinds boost the ground speed, resulting in a faster traversal. However, crosswinds during cruising flight can cause a divergence between the glider's heading and its track over the ground. In the context of landing, the wind's role intensifies. Headwind during landing reduces the ground roll, facilitating a shorter distance for the glider to come to a stop. Conversely, a tailwind increases the ground roll, demanding a longer distance for a safe landing. Crosswind landings require pilots to compensate for drift using proper flight control inputs, such as sideslip or crab techniques. The nuanced interplay of wind during final glide, particularly in the presence of crosswind, demands strategic adjustments from the glider pilot. Keeping the glider's nose pointed somewhat upwind of the target on the ground is crucial for maintaining a correct approach angle. This correction ensures that the glider's heading aligns with the target on the ground, enhancing precision during landing. It's noteworthy that wind conditions impact the glider's rate of descent and approach angles during landing. The pilot must adapt to different ground speeds induced by wind to ensure safe touchdowns in the landing zone. Adjustments in the traffic pattern and modifications in procedures become imperative to compensate for varying wind conditions. During landings in gusty conditions, the wind gradient phenomenon comes into play. Abrupt changes in wind speed near the surface can result in a loss of airspeed, requiring the pilot to make rapid adjustments to maintain flying speed. Flying a faster approach becomes essential to counter the effects of wind gradient and ensure a safe landing. Understanding the intricacies of wind near the ground is crucial, considering its altered behavior due to factors like thermal formation, turbulence, gusts, and lulls. Wind gradient introduces an additional dimension to landing considerations, especially when turning steeply at low airspeeds and altitudes near the surface. Vigilance and caution are paramount to prevent unintended roll behaviors induced by wind gradient. In conclusion, wind is a formidable factor influencing glider performance throughout various flight phases. Pilots must assimilate these wind effects into their decision-making processes, traffic patterns, and landing techniques to ensure the safety and precision of glider operations. If you click like and subscribe and leave a comment, we will provide a coupon for a free PDF download, one of 9 ebooks. However, each individual can only download up to 1 out of 9 ebooks for free.